Thank you for making me feel that old. Okay, so my name is Pierre. Those who work in the Scala community might have seen my avatar or this username somewhere. I'm a tech lead at DevSisters. That is a South Korean gaming studio. So I work mostly in the game industry. I've been using Scala for about 12 years now, and I'm active in the Scala open source ecosystem. I created some libraries such as Caliban and Shardcake. So my company makes multiple games, but the main one and the one I work on is called CookieRun Kingdom. It's been live for over 4 years, and it's a mobile action RPG with some social features. It has over 70 million players worldwide, mostly in Asia, also in the US, and there are translations for many languages. And the game servers for this game are entirely written in Scala in a pure functional programming fashion. So my motivation for this talk dates back from maybe 6 months ago, and I guess I was spending too much time online, but I felt that on discussions in Reddit and Twitter, there was quite a lot of negativity, like people are arguing about what the language should be and what not. And I felt a little bit of a dissonance with my experience at work because I've been using Scala for many years and for quite complex games with a lot of users. And for me, Scala and functional programming really works in practice. I wouldn't trade it with anything else. And I thought that would be nice to show how we are using it in practice, how we can build real-life applications with a lot of users. So I'm going to deep dive into a new feature that I had to implement last year. I'm going to talk a bit about the architecture that we chose and then how we designed our application and some implementation details. Okay, so flashback to a year ago, we got a new request from our game designers to build within our game some mini games that were multiplayer and real-time. So what that means is that our players could go to some place in the game and say they want to start a mini game, and then they get matched with other players. So depending on the game, it's like 4 to 20, and then they play a little game with these players, these other players, usually for 2 to 3 minutes. And when I say real time, it means that they can see what the other players are doing. They can see the other players' movement, and other players' action can impact them, and so on. So that is a little bit different from what our usual game is, where it's more like single play. Mostly players are doing actions on their own. So we had to think about some different architecture. And for these mini-games, the latency requirement was more important than usual because you had to be able to see other players' actions in real time. So here are a few screenshots showing like the mini-games that we developed. Some of them are a race, some of them you have to catch monster before the other players, and so on. Okay, so let's talk about the architecture first. How did we handle the load and these multiplayer problems? One thing to note is that because it's an existing game, we know that on the day one where we release that new feature, we're going to receive a lot of load from a lot of players. So our typical architecture for the existing game is distributed actors. So we have actors for concepts such as users or guilds, and those are distributed over a cluster of servers. And we are using sharding and message passing to send messages to a given actor. And a given actor is only alive in one server over the cluster. If you're familiar with Akka or other similar solutions in Erlang and whatnot, I guess you're familiar with these concepts. We are using a library called Shardcake that we developed at DevSisters and open sourced, but it's conceptually similar to Akka cluster sharding. So here's an example. You have a user one that does some game action. They send a request to a random pod, let's say pod 1. But because the actor for user 1 is alive on pod 3, the pod 1 will send a message to pod 3, to that actor, and then the actor will process the message and return a response back to the client. If at the same time another user, for example, user 2 wants to add user 1 as their friend, for example, they're going to send a request to our servers. Maybe it will go to pod number 2, but pod number 2 will also send a message to pod number 3 to the same actor. And that actor will process the messages sequentially. So even if they have arrive at the same time, they will be processed sequentially. So this is our typical architecture so far. So our first question was, can't we just use that for that new requirement? But we had concerns about the latency because, as you could see in the previous diagram, there is some internal communication. Like whenever there is a request from the client, it goes from one server to another server, and like we are wasting a little bit of time there. There are also some issues that can arise when you use auto-scaling. For example, you are adding new pods or removing pods depending on your load. When that happens, the shards needs to be rebalanced. So actors are moved from one pod to another so that all pods have a balanced amount of actors. When that happens, it means that we need to stop an actor, all the actors from one pod and start them somewhere else. And it creates a little bit of latency. So in single play, it's okay. Maybe one request will be a little slower to respond. That's not a big deal. But for this use case where we have to see the player's movement in real time, that might be weird. Like you might feel it on the client side if suddenly like everyone stops moving. Another concern that we had was we wanted a multi-region deployment so that users in Europe could play with other users in Europe and with servers also in Europe so that the latency would be minimized. And while we can do this with sharding, this would add some additional complexity. So we took a different approach, and with our main goal being to reduce the indirection, like remove the steps between the client and the actual server logic. So we used something, different strategy called dedicated game servers. So what it means is that instead of having our group of servers and actors here and there, when we are ready to start a game, we actually spawn a game server on demand, a very small game servers with limited resources, because a game server is only responsible for a single game. And that game server is alive for the duration of the game. When the game is over, we just stop it. One benefit with this is that game clients directly connect to the actual game server where the server logic will happen. There is no intermediate. For that, we used an open source platform called Agones, developed by Google on top of Kubernetes. And that makes it easier to like spawn these game servers on demand. Here is a little diagram. So the flow is that the client first connects to a matchmaker service that is going to like wait for enough requests from different clients to group users together. And when we are ready to start a new game, the matchmaker will communicate with the Agones controller to say, like, give me a game server. And Agones has what we call a fleet of game servers. There are a number of game servers that are already ready to be used. They are doing nothing. And it will pick one of these game servers and then allocate it to this game. Then it will return the IP and the port of that game server to the client, back to the matchmaker and to the client. And the client will connect directly to that game server. And that fleet, we can control the size of that fleet, like how many servers we want to be always ready. We can configure some percentage to say, like, we want 10% of the whole number of game servers to be like in the ready state, and it scales automatically for us. So the advantages of this architecture is that we reduce the latency between the client and the server. Obviously, there is no intermediate anymore. It's very easy to deploy this in multiple regions. The matchmaker can just say, like, I want a server in this region. We just need to have a Kubernetes cluster in each region. It also really simplifies the game server implementation because we don't need to handle like multiple games. Just one game server is one game. There's one state. That's very simple. And it also makes deployments very easy. With actors, distributed actors, you need to do rolling update. And then for some time, you have like an old pod and a new pod. And if your serialization protocol doesn't support like the old way, you might have errors, and it takes some time. Here it's much simpler because when we have a new version of the server, we just change in the agonist configuration what's the image of the server. And all the new game servers that are spawned will use the new version. And for the existing servers, those that are already in the middle of a game, we just wait the game to terminate. They keep the old version. And since a game only takes about 3 minutes, it means that after 3 minutes, all the game servers are already using the new version. So we can go from a bug fix can go to production in literally 5 minutes, excluding QA time. The negative, there is an operational cost to have this agonist cluster set up, but in our company we operate multiple games, and there were already some other games that were using this architecture, so our DevOps team is already very familiar with that. Another downside is there is no redundancy per game. So with actors, if a pod just dies, the actor will be restarted somewhere else automatically. But here, if your game server just dies for some reason, the clients will be disconnected, and then that's it. But we kind of accepted that because this happens very rarely anyway. And we just built some kind of refund mechanism so that if a game server doesn't report its result within some amount of time, let's say 10 minutes, because it's supposed to finish within 3 minutes anyway, after 10 minutes, if it doesn't report a result, the main game server will just refund the players from their entry ticket. And that's it. And it does really happen extremely rarely anyway. Okay, so this is for the architecture. Now let's talk more about the application design, like how did we organize our application. This is a very rough schema about the main 4 layers that I'm going to talk about. We have domain entities, domain logic, API, and repositories. I'm going to mostly focus on domain entities and domain logic. Okay, so first, domain entities. It's a very important part of the system. It's usually the first one that I work on when I receive requirements from the game designers. This is mostly just data that represent our domain model. It is fully immutable, and so case classes, enums, and whatnot. We also add some small helper functions for very simple transformations or calculation related to those data types. We try not to put domain logic in there. So it's usually like one-liners, such as in this example, we have a tile with a row and a column. We have a distance method to calculate the distance to another tile. This is simple enough and reusable enough that we just put it in there and not in the rest of the domain logic, but that's kind of the most that we put in there. One thing that you may notice is that the row and the column types are not ints, but they are specific types. That is because we use new types, which are type aliases that hide some underlying type, so that we don't mistakenly pass a column as a row or a row as a column. We used to have, this used to have some kind of overhead in Scala 2, but now in Scala 3 we have this really nice feature called opaque type that just does exactly what we need. So you can define an opaque type row equals an int. In the file where you define this, those 2 types are equivalent, but in the rest of the code, a row is considered as something unique that is not an int. You can use the next syntax, which is a row is a subtype of int, so that if you have a function that takes an int, you can pass a row, but not the other way around. Okay, so new types are nice, but we actually go further than that by using refined types. So the goal for refined types is to add some conditions so that our types have some like boundaries, for example, and that it's impossible to create a type that does not satisfy those boundaries. So you can do that with opaque types, actually, but there are some libraries that make it much easier. So libraries like neotype and iron just cut down on the boilerplate and add some smart constructors, and they have some nice macros that make it nicer to use. Here's an example. So we have this object row extend subtype of int. So here, in this case, it's a subtype. I can also use new type of int if I don't want it to be a subtype. And we define this validate function that says like our input should be higher than or equal to 0 and lower than 25. And then if I try to create a row with a value of 10, it works, no problem. If I try to create a row with a value -1, it does not compile. I get a compile time error with a nice error message that tells me exactly why it doesn't work. And if I'm trying to construct a row at runtime from a value that, let's say, comes from the client, the row construction will return a different type. It's going to be either a string error or a row. So it's impossible to construct a row that doesn't fit these conditions, which means that in the rest of my domain logic, I don't need to care about checking those boundaries anymore, which make the rest of the code nicer. Okay, so now let's talk a bit about the API. So as always, when working on servers, we need a clear definition of the API that is exposed to the client so that changes to these APIs are explicit. There are two strategies that are commonly used in Scala and in other languages. Code first, which is we create some endpoint definition or like endpoint if we use HTTP or resolvers if we use GraphQL. We create that in Scala and then it generates an open API spec or GraphQL schema spec from that. The other approach is to define a schema first in some language, like usually language agnostic protocols such as protobuf. And then from this schema definition, libraries use code generation to create Scala code matching those schemas. In our case, we use protobuf, so we went for the second option. So here is a basic example. We have a protobuf definition for a message style that has a row and a colon. And then the Scala PB library, at compile time, we generate Scala code. So it's going to generate this case class style that contains a row and a colon. Now, you might think, I just showed you before I had this nice style case class that was using refined types, but the code generation generates this class that doesn't have refined type because it doesn't know about it. And we don't want to use this class in our domain logic. We want to use the nice one with the refined types. So we use transformers so that when we receive a call from the client, it comes as this code-generated format. We transform it to our nice domain entity using Chimney, a library for transformers. And Chimney is able to transform from one type to another as long as the types have the same shape. So by same shape, I mean the same fields. If they are named the same, it's able to convert from one to another. If they have different names, you need to tell it like this is the name in this one and it's that name in the other one. But if they have the same names, it's automatic. And when it comes to the types, it needs to know how to convert from an int to a row or an int to a colon. But thankfully, because we use neotype for the refined types and neotype has support for Chimney, we just need an import and then it knows how to handle transformations from neotypes types and the underlying type and back and forth. So Chimney allows us to avoid a lot of boilerplate and keep our domain logic with only the nice domain entities that we want to work with. Okay, repositories, I'm going to be very, very quick on that part because this is a very widely adopted best practice. That is, we just use interfaces whenever we need to communicate to the outside world, such as an API, a database. We just have interfaces, and then we have live implementation, test implementation. This is widely adopted even in other languages, so I'm not going to talk too much about it. Let's focus on the more interesting part, which is the domain logic. All right, so when we think of the domain logic for this game, what does it actually do? The first thing is what I call the rules of the game. We have our game, we have a state, and then there's a player action. We need to calculate like what happens. Like if this is our state, this player does that, then this should happen, and the other players should see that. That's really the rules of the game. Then we have, this is a multiplayer game, right? So we have a state, but we might have concurrent requests to access or modify that state. So we need to handle this concurrency aspect, and how do we share the state between different players. And then finally, our domain logic also might need to communicate with the outside world. We might need to call another API, we need to call our repositories, communicate with the client, so we have to do all these kind of things. So if I categorize these three items, we could say that the rules of the game is just pure logic. It's just, if this happens, then do that. And then we have, on top of that, we have our state management. And then on top of that, we have our side effects. And that's how we designed our application into three different layers with a pure domain logic core, and then the state management, and on top, the side effects. Now let's focus on the pure domain logic. Again, what do we need to do in that part of the code? When we receive a request from a player action, first we need to validate it. Like, is that player allowed to do this action? If they are here, can they move over there? Or like, if they are using an item, do they have this item? And so on. So if not, we need to fail and reject the request. Then we need to read some kind of configuration because the game has a ton of parameters, like the list of items, the list of tiles, the location of things. All of this is defined by our game designers, and they work on this in actually Excel file, and this gets turned into protobuf data that we can consume as a server. So we need to read that configuration to know where everything is and so on. Then we need to access our state. We need to modify that state depending on the player action. And finally, we need to accumulate some output, because when players do things, we need to tell the other players, like, this happened. So we have to produce also some output. One important thing, in this part of the code, we don't allow any side effects. We just allow the four things that I listed. Side effects are moved in another layer of the system. So if I translate these different actions into more general effects, we can say that our domain logic needs failure effects, a reader effect to read the configuration, a state effect, and a writer effect. And this part of the code does not allow the IO effect, which is an arbitrary side effect. So if we rewrite this as code, we could say that our domain logic should have the following shape: a function from an initial state and a configuration to an output which has a list of events. This is our accumulated output. And then either an error or a new state with a response arbitrary of type A. However, when we write our code, we don't want to have every function with this signature, because that would be very inconvenient if every time we call a function, we have to unpack the list of events, the error type, like, is it an error, then I should stop or I should continue. If I have a list of events and I call another function, I need to combine them together. Like, that would be quite cumbersome. The performance also would be not great, because we would have to deconstruct these tuples and this either and then reconstruct them all the time. That would be also not stack safe. So instead we use a monad. So in our project we use a monad, a data type called zpure, which comes from the library ZeoPrelude. And this is a monad that does exactly the four effects that I mentioned earlier: error, reader, writer, and state. It only does that, so it only allows these actions and nothing else. So it's actually perfect for us. There are some alternatives in the Scala world. The most interesting ones for me are Kyo and Turbolift. Both of them have a bit different approach. Like, zpure is hard-coded to these four effects. You always have them, and you can only have them. But with Kyo and Turbolift, you can have any number of effects. You're not limited to these four. You can have more. You can have two different states. You could omit one of them. So it lets you control, like, what effects you have. One downside of this is that because zpure is hard-coded to these four effects, those effects know about each other. So, for example, when you have an error and you catch the error, the state will be reset to the value it had before the block where you catch the error. You can also clear the events in case of error. While with QA and TurboLift, the effects don't know each other. So when you catch an error, it does not affect the state at all. They are independent. So you need some extra work to make it work. Okay. If you're curious about QA, I invite you to see Flavio's talk tomorrow about it. One thing to note is that when you don't need these effects, like every function that doesn't need to access like the state or to have an output event, we don't use the monad. You can directly return pure values or you use function or either. Like we don't use this when we don't need to. Okay, so here's an example of how our code looks like. So we have a lightweight DSL on top of Zpure, so we don't use Zpure directly. Two reasons for that. One is that by hiding Zpure, we hide the kind of technical detail, and if we want to switch Zpure to something else someday, we could, and we will not need to modify the rest of our code. And secondly, Zpure often requires an explicit state type parameter, which is a little annoying because in our case, the state is known in advance, so we don't want to specify it every time. So instead, we use our own functions on top of Zpure. Then we implement our logic using these functions. So update player, use the update that changes the state. Get player will read from the state. Dot sum or fail will fail if we didn't find the user. Then validate change style. We'll use also failure in some condition. And finally, this is how our pure domain logic looks like. And it's very simple, finally. Change style, we have some parameters. They're all like new types and refined types. And then it's a simple workflow. Like we get the player. If we don't find the player, it's going to error and stop there. We validate, we can change the tile. Then we update the player, we change their tile, where they are. And then we log. Log is the produce an event that will be later sent to all users. So this is how our domain logic looks like. I think the benefit from this approach is that there are only a few things you can do, finally. We only allow these few actions. And this gives us the ability to focus 100% on the domain logic when we write code. When you see that code, there is no concern about anything else. It's just about the rules of our game. It's also very easy to test. We can just run any function by giving it a state, a starting state and a config, and then we get the events and then either the error and the new state as a response. Okay, so now let me talk about the state management. As I said, we have concurrent accesses from different players, try to modify our state. In this part of the code that is built on top of the pure domain logic, we also do not allow side effects other than modifying our state. Usually in functional programming, we have the concept of ref, which is a functional mutable variable. But instead of using ref, we use STM, which stands for software transactional memory. And I'm going to show an example of this. I think this is an interesting concept that is often hard to grasp because most of the examples online about STM show usage of transferring an amount from a like bank account, like a debit and a credit happen in a transaction. And I always found this not super useful because you would never store a balance in memory. It's always in a database of some sort. So this example does not seem super useful. However, STM can be really useful in practice, and I'll show you when. So let's say this is our state. We have a case class state. It has a game state, which is really about the players and their items and their tiles and so on. And then we have these like connected users, refunded users, rewarded users, disconnected users, which are all kind of things that we need to track for our game logic. Like we need to know which users are currently connected, which users were already rewarded so that we don't reward them a second time, and so on. So first option, we can put this whole state in a ref. And then whenever there is a request, we do ref.update and update the ref. There are two flavors of ref in the Zio library, which is what we are using. One is optimistic, so that if there are two concurrent requests, the first one will succeed, then the second one will fail and will be retried. This works great, but when you have a lot of requests, you might have contention. If there are a lot of threads or fibers trying to modify that state, maybe many of them will fail and retry, and then you get a lot of contention and it becomes slower. There is also ref.synchronized, which is more pessimistic. So this one uses a semaphore in front of all the state modification so that there will be only one happening at the same time. So in this case, there is no issue with retries, but it is rather slow because you can have only one concurrent access to your state. Another option would be to use a ref for every field of our state. That way, if someone wants to modify connected user IDs and someone wants to modify rewarded user IDs at the same time, there is no contention there. However, if you have a workflow that is refound all disconnected user IDs, you start having problems because you need to access one ref and then modify another ref, but those operations are not atomic. So maybe after you modify the first one, you modify the second one, but the first one has already been changed by something else. So this is not, you cannot have transaction between different refs. Unless you change them to T-refs, which is something that comes with STM. Again, we are using Zio here. So you can change every ref to T-ref, and if you have a ref of a map, you can change it to T-map, and ref of a set would be changed to T-set. And then you get almost the same semantics, except that now you can you can combine operations together. You can get something or modify disconnected user IDs and then modify refunded user IDs, and that gives you an STM type as a result. And then you can call commit to actually commit the whole transaction. And this is atomic. And then, same as with ref, if you have two transactions at the same time, the first one will succeed, the other one will fail and will be retried. But only if they really conflict with each other. So if they are using different T-refs, then there is no problem. If they are using the same one, they might conflict. But something that is really nice here is that if you use T-map or T-set, if you have transactions that change different keys in your map, they will not conflict with each other. So let's say you have one fiber trying to add someone to refunded user IDs, and another one is removing another player from refunded user IDs. Those two transactions do not conflict with each other and do not cause any retry. So this is quite performant and really reduces contention in regards to state access. Okay, so we have our pure domain logic, our state management. Then on top of that, that's where we write effectful domain logic. That's the part of the code where we are allowed to use side effects. So we need to interact with our APIs, which is usually, like in this case, a gRPC stream. We can call our repositories. We can also use concurrency primitives if we need them, like such as a queue, a promise, a hub. We can fork fibers to do things in parallel. We can also do logging here, start timers, and so on. Here is an example taken from our code. That's what we do when we start a new game. So we do some logging. We get the list of allowed user IDs from a metadata store. We get our game configuration from the main game server. Then we initialize our state. We fork some fibers to start our main game loop, start some timers, and then complete a promise that will allow the players to send us some game actions. We also have error handling here. So in case of error, we log something, and then we try to refund the missing player who didn't get refund yet. So the main point with this is that this code is, I think, the most complex part of the system. What we saw before is relatively simple. It's just like simple flows, like nothing really unexpected would happen. But in this part of the code, unexpected things can happen. Like you can have timeouts, you can have errors from whatever third-party API you are calling. So the goal of this architecture, the goal of the way we design the system is that we keep this part as small as possible. We try to push everything that we can to the other layers. So what we can move to the pure domain logic, we try to move it in there. some validation is moved to entities using the refined type. Things are moved like also to repositories when possible. And the goal behind that approach is to make each part easier to reason with. I think a mistake would be to try to mix. If you mixed everything together, it would be quite complicated. If you mix the game logic with the side effects and the state management and so on, it would become quite harder to maintain. So that's why we use this approach of 3 different layers. So even though the effectful domain logic appears here as the center of it all, we really try to push things to the other layers. Okay, so to conclude, we have now built 4 mini-games with this architecture, and we are really happy with the reliability of this system. When we launched the first game in production last year, we had maybe 2 bugs in production that we had to patch. One of them being mostly a miscommunication between the client and the server. The other one was a real bug. But for the next 3 games that we developed after that, we had exactly 0 hotfixes, 0 bugs found in production. And it only takes like around 3 weeks for a developer now to build a new game, which is relatively low. And I think this is really because the code is approachable and quite easy to understand because of that separation that we did. So I would say that the key takeaways from our experience building this new feature is that I encourage everyone to leverage the type system, especially in Scala, to make the code safe and self-documenting. It's a very powerful type system, and we can really rely on it to avoid a lot of mistakes. Then I really like to keep the core domain logic pure and testable. Of course, it depends on the domain that you are working on. If your domain logic is just calling a bunch of third parties, it's hard to do that. But in other fields, such as games, where we have complex rules, but I'm sure there are other fields where this is applicable as well, it's really good to keep this isolated and free of side effects. And again, try to isolate the side effects to the edge of your system. All right, that's it for me. I think we have 5 minutes left, so if you have any questions, feel free to ask. Otherwise, you can find me around. Feel free to talk to me until the end of the conference. Yeah, thank you.
Applause. Now, it's question time.
Well, I could have gone downstairs, but thank you. Okay, so my question is, what technology is used on the client side? Because is it some standard game engine that's used in many other games like Unity or something else?
No, the client is using Unity, but the server doesn't at all. We don't use any game engine. It's just we process client requests.
Mm-hmm.
And,
right, so I'm wondering, what was the path to the decision that you don't want to use the server component of Unity, that you're going for a completely custom solution? What was the thought process behind it?
Actually, we did not really feel that we needed it. We are not using, like the server side is not really controlling any like visual aspects. It's really just processing game logic, such as like what I said before, but there is no like movement or like 3D computation and whatnot on the server side. This is just on the client side. The server is just there to control, like you are using this item, you are moving here, moving there, and so on. So we don't really need anything like that, for that game at least. I know it's different from some other games, but for these games, yeah, there is not really any need for that.
Mm-hmm, understood. And the second question is, so you're saying that this component in Scala for the mini games is like the first usage of Scala overall in this project, or is it just or the other components that you're using, like matchmaking and other stuff, is also using Scala?
We are also using Scala. This is a new component. Actually, initially, we used to be the main the main service was in Scala 2. This one we built as Scala 3 directly because it was separate. We since have moved to Scala 3 on the main one, so now the code is more lined between them. But yeah, we have been using Scala all along.
Okay, thank you.
Are there any more questions? Nope. Okay, so just another round of applause.
Thank you.